Hi there, my name's Professor Deborah Davis. I'm the Professor of Midwifery at the University of Canberra here in Australia. In this session we're going to focus in on confidence intervals and also p-values. In the last session we examined odds ratios and relative risks, and we used this example. If a woman came to you as a midwife and asked you if she used a pool for water immersion in labour, would that mean that she'd be less likely to have an epidural? Now, in the last session we focused on this little bit here, the odds ratio, and we also looked at relative risk. So we came to understand that what this means is that her odds of having an epidural would be less if she used water immersion in labour, and that's because this value is less than 1, so there's less of the outcome. But I did alert you to the importance of what comes next in the bracket, and that's what we'll focus on in this session. This stands for 95% confidence interval, and you can see that in this case the range is from 0.70 to 0.98, and we'll find out what that means as we move through. So in research we're usually interested in understanding whether there are differences between groups on some important measures, particularly outcome measures. One group may be exposed to something, have a new treatment, a new drug, a new intervention, and we're comparing it with another group who's not having that same intervention or exposure. And what we want to understand is whether any differences that are seen in those two groups are a result of the intervention they've had and not something else. So was drug X effective in relieving a person's pain? Because some differences do occur by chance. Now let's look at this example. We're interested in usually a whole population. So would this drug work on a population of pregnant women, for example? But we can't research usually a whole population because of resource implications, feasibility implications. So in research you draw on a sample, and it's a sample from that population, but it doesn't necessarily have the same characteristics as the whole population. So let's look at an example of, say I had a bag of jelly beans. That's the whole population. And I know that there are 100 in there because I put them in there, and I know that I put 50 red and 50 yellow jelly beans in this bag, you can't see through the bag. Now I ask you to take out a sample of 10. You reach in without looking, count off 10 and pull them out. It's really unlikely that you're going to have the same proportion in your hands of red and yellow as that whole population, because you've only pulled 10 out. So you might have, for example, 7 red and 3 yellow. The proportions don't match what the proportions are in the whole population, and it's because it's a sample, and it's a fairly small sample. You've only taken out 10. So let's take another example. Say we had the whole population we're interested in is 11 million adult males, and say we knew what their mean height was. It was 180 centimetres. But we did some research just with a sample and we measured 1,000 adult males. We might get a mean height of 176 centimetres in our sample. So that's not the same as the mean height of the whole population. So we have to accept that there are going to be some differences between the whole population and the sample in any research that's involving a sample. So what we want to try and understand very often is what is the probability that the findings that we got, the differences in groups in a piece of research, were due to chance and not to the exposure or the new drug or the new intervention that one of the groups were being exposed to. And this is what is known as the p-value. So formally, it's the probability that the observed relationship between the variables, or the difference, occurred by chance, and that in the population from which the sample was drawn, there was actually no such relationship or difference. So if in our research comparing in a sample, comparing whether drug X has any impact on pain, we want to know if our research showed that there was a difference, what's the probability that that difference occurred by chance and it wasn't actually due to the new drug that we were testing out. So in health studies, we usually set that p-value by convention at least 5%, sometimes even only 1%, depending on the type of study it is. So if it's set at 5%, that means that we'll call something statistically significant if the p-value is less than 5%, but we won't call it a significant difference if it's greater than 5%. So we're willing to accept a 5%, but no more. That's a 1 in 20 probability that the result that we got occurred by chance. So the greater the p-value, the bigger number, the less convinced we are that there's a true relationship or difference, because there's a bigger probability that that difference came about by chance. So when a result demonstrates a p-value of 0.05 or less, that is said to be statistically significant. So if we just have a look at the examples down the bottom here, which ones do you think would be a statistically significant p-value? So there they are in red. If a finding gives you a p-value of 0.06, that number is bigger than 0.05, so we're not happy to accept that as a statistically significant finding, because there's greater than a 1 in 20 probability that that result occurred by chance. The next three, they're all less than 0.05, less than 5%, so we would consider results that had a p-value of 0.049 or 0.01 or 0.005, we would call those statistically significant findings. So let's have a look at an example. This table comes from a study that looked at different modes of birth for women who were planning to have their babies in different sort of places. So we can see down the left side here we have the different modes of birth: vacuum extraction, forceps, emergency caesarean section, and then we have the groups that are being compared. So we're comparing women who plan to have their babies at home with women who are planning to have their babies in a primary unit. We can see this as a reference group, so all groups are compared to this group, the women planning to have their babies in a primary setting like a birth centre. Then we can see the secondary hospital as compared to the primary, and a tertiary hospital, which is a higher level hospital compared to primary. So we'll stick with the crude relative risks in this column, and previously we've understood that a relative risk of less than 1 means less of the outcome. So women who were planning to have their babies at home were less at risk of a vacuum extraction than those who were planning to have their babies in a primary unit. And we also saw that relative risks greater than 1 meant they were at greater risk of the outcome. So this group with a relative risk of 4.5 has 4.5 times the risk of having a vacuum extraction compared to women who are planning to have their babies in a primary birth unit. And the tertiary hospital group are 8 times at risk of having a vacuum extraction compared to the group who are planning to have their babies in a primary unit. But the other thing we did I alerted you to last time was that this bit in the bracket here is really important. This is the confidence interval. We'll come back to that, but if we go across to the last column, we can see the p-values. So the p-value for the home group, while this is telling us they have less risk of the outcome, the p-value is greater than 0.05. So this isn't a statistically significant finding. There's really a high probability that the difference between the home and the primary unit groups happened by chance. It wasn't due to the fact that they were planning to have their babies in different places. So that's not a statistically significant finding. But if we move down to the secondary hospital, so the secondary hospital outcome compared to the primary, this number is less than 0.05. So this is a statistically significant finding. So we can say that this difference between the secondary hospital and the primary hospital group is statistically significant. And same for the tertiary hospital group compared to the primary. The difference in the outcome, which is the vacuum extraction, is significantly different. If we come down again to the next one, if we're looking at forceps as an outcome, we can see that the home birth group compared to the primary unit group, this is not a statistically significant finding. This difference between the home and the primary group could have happened by chance. And you can see the actual number here isn't very far away from 1, is it? Which was, remember, the line of no effect, or 1 means there's no difference between groups. But this isn't statistically significant. But again, the tertiary compared to the primary is, and the secondary compared to the primary is, and the tertiary compared to the primary, they are statistically significant. And same for emergency caesarean section. The difference between the home birth group and the primary unit group isn't significantly different, but the other two are. Okay, let's just think about confidence intervals for a moment. So really what a confidence interval does is it just builds in some room for error. So we might gain a result like an odds ratio of 0.89 or whatever it might be, or a difference in height or weight for two different groups. But because we're dealing with a sample and we're not dealing with a whole population, we have to build in a little bit of a margin of error around that result that we got, and it's called the confidence interval. It's worked out in the statistical packages that will do the statistical analysis for you. But we also, it's something we set by convention, so we're usually set it at 95% or 99% in health studies. So a 95% confidence interval indicates that we're about 95% sure that the true value for that whole population lies somewhere across this range. So we do accept that a result that we get in a sample isn't as precise or doesn't reflect precisely what we would find in the whole population, but we're 95% sure that the result of that whole population would be somewhere in this range, and that's the confidence interval. So if we look at this example, if we had a mean height in a sample of, say, 100 people, and we worked it out to be 180 centimetres, and then the room for error there, the confidence interval, is plus or minus 12 centimetres. So if we put that around either side of 180 centimetres, it means that the true value, while we got a result of 180, could lie anywhere from between 168 centimetres up to 192 centimetres. Then if we did another study, but this time we had a sample of 10,000, which is a much bigger sample, we might find that the mean height of that group was 172 centimetres, but the margin of error here is only plus or minus 4 centimetres. So you can see that in a bigger sample size, usually that confidence interval shrinks in a little bit more, so that the result you're getting is a little bit more precise. Our result was 172 centimetres, but it could go anywhere from 168 to 176 centimetres. We don't know really where the true population result lies, but it's somewhere within that range. Now, not only do continuous data like heights or weights have a confidence interval, but things like the odds ratio and the relative risk can also have a confidence interval. So in our first example, we have an odds ratio, say it was 1.27. We learnt in the last session that that means a group have greater risk of an outcome, whatever it was that was being studied in this case, because the number is more than 1.27. But the true odds ratio for the whole population is estimated to be between 1.07 and 1.47. So while we got a result of 1.27, really we have to understand that the true result is somewhere within that range. In the next example, we have a relative risk of 1.5, but when we put the confidence interval around it, it could be anywhere between 0.8 and 2.02. So the relative risk, if this was dealing with the whole population, is somewhere within that range. So let's use this example. It was a study. It's a little bit blurry, the table, I'm sorry. It was looking at the outcome of intrapartum death by intended place of birth again. I think this was a Dutch study. If we can see the first row, hospital, has a number 1. So this is a reference group. So everything else is compared to this hospital group. So we're comparing the risk of intrapartum death for women who are planning a hospital home birth compared to those planning a hospital birth. And if we go along to the relative risk here, the crude relative risk 0.83, that tells us that the home birth group are at less risk of the outcome, which is intrapartum death, compared to the hospital group. How much less risk? Remember, we had to take this number away from 1. So 1 minus 0.83, it's about 17%. So about 17% less risk of the intrapartum death in the home birth group. But we do have to figure in now this confidence interval. So let's try and draw that. So what I've done in this graph here is I've drawn a line down where the number 1 would be, and it's a really important line because in the last session we learnt that an odds ratio of 1 or a relative risk of 1 means there is no difference at all between the groups. So it's called the line of no effect. Now I've put in this horizontal line here the positive values on a scale and some negative values on a scale. So we've got an odds ratio that we're plotting here, the 0.83. It's less than 1, so it's on the negative side. And you can see I've plotted that about where 0.83 would be. But we also have to draw in the confidence interval. So we need to draw a line from 0.60 to 1.13. So I've estimated about where 0.6 would be, and I've estimated about where 1.13 would be, and I've drawn that line. So even though in this study the computer calculated a relative risk of 0.83 at here, whoops, beg your pardon, the true result could in fact be anywhere along this line. It's just as likely to be here at this end as it is here at this end. So while this is our point estimate, we have to appreciate that it could come anywhere along this line. So that's quite interesting in this example because the line runs across the 1 and occupies the space on the positive side and the negative side. So it means that really the risk of intrapartum death for the home group compared to the hospital group could be less if it occupied somewhere over here, or their risk of intrapartum death could be more if it occupied something over here. So in this sort of situation, whenever the confidence interval crosses 1, it's never a statistically significant finding. We don't have a p-value here, but I can tell you it's not going to be less than 0.05. That's not a statistically significant finding because the result could be less, could be more, which actually tells you nothing very much. So this is an example that we used at the beginning. If a woman asked you if she used the bath pool in labour, would that mean she's less likely to have an epidural? We understood that this part, the odds ratio, is telling us that she has less risk, but we need to more fully understand the confidence interval. So if we were to draw this one on the same sort of chart, I've got a bit of a different scale, but same idea. We've plotted the point estimate, which is 0.82 at here, and we've drawn in the confidence interval, which goes from 0.70 to 0.98, which is very close to 1, but it isn't 1, it's less than 1. So you can see in this example, the confidence interval doesn't cross the line of no effect, which is 1. So while the true odds ratio could be as little as 0.98 or could be as much as 0.70, it still falls wholly on the less than side. So at its greatest or least value, it still indicates less of the outcome. So this, we don't have a p-value for this one, but this would be a statistically significant result because it is clear of 1, which is the line of no effect. So if you carefully have a look at the confidence intervals for each of the results that we had a look at a little bit earlier, you can just take note of the ones that do cross over that line of no effect. So this one goes from a less than 1 result to a more than 1 result. It crosses over that line of no effect, doesn't it? And you'll see that the p-value is not significant. In the next example, you can see it goes from a positive result of 3 through to a positive result of more than 6. So if we were to plot that, it would be clear of the line of no effect, and that is a positive result. We have a look at another example. This is quite a broad confidence interval. It goes from 5.6 up to 11, but it's well clear of the line of no effect. So it's a statistically significant result. And you can follow those other results down, and you'll always note that if the confidence interval spans from the negative to the positive and crosses over 1 even just a little bit, then the result's not statistically significant, and that means that you can't say there is a difference between these two groups in terms of their outcome. So that's the end of this session, and I hope you found it useful. One of the sessions that will be coming up, we'll look at those chartings, which are called forest plots, in more detail.